Okay, so you should have completed part one and part two of the paper. But hopefully you recognize that the graphs probably are not reflective of what's going on in New Jersey right now. The parameters were given before we had the data we currently have. So to have a good model, to model what's happening in New Jersey, some changes need to be made. I'll leave it to you to research and come up with some hard numbers to work with, but I want to at least get us in the ballpark. So I'm going to switch over to MATLAB here. Okay, and here's where we left off. So with the parameters that are given to the right in the code and the graph that was produced from those parameters. It's nice because you can visually see what happens when we start our interventions at week 10. We can see how the curves abruptly change shape at week 10. And week 20 was where we were going to stop the sort of the hammer phase. We're going to sort of end some of the lockdowns, ease restrictions, and we can see that there's another sort of quick change in the curves right around there. We can see it in the recovered curve, the purple curve here, and in the susceptible curve, it's kind of hard to see what's going on in the other curves because of the scaling, right? So it looks good, but the numbers aren't realistic at all. So let me explain why the numbers aren't realistic, all right? So let us, first of all, try to figure out where we are in the curve. Okay, so right now we're at about week 14, all right? We're 4 weeks into our stay at home sort of lockdown, so we're at week 14. And we have some hard data that has come in, all right? Probably the most reliable data is the data on fatalities because with limited testing, our knowledge of how many people are infected at the present is dubious at best because most people haven't been tested. It's a very, very small percentage of the population that has been tested at all. But you can be pretty sure that if there's a fatality, we have a pretty accurate measure of that. So we want to see if our fatalities at week 14 are anywhere near a realistic number. Well, first of all, how do we find week 14? Okay. The key is, if you look down at our time step, it's 0.01. So that's 1/100th. So that means to plot our data, we took 100 time steps per week. So week 14 would be about 1,400 time steps. In fact, we can check that out. We can say, what is the time at 1,400 steps? And you can see that it's almost 14. If we wanted it to be 14, we actually have to just add one more on. So if we use 1,401 steps into the model, we'll know what's happening at week 14. Okay, so the key number is when we're at 1,401 steps, we are at week 14. So now let's try to figure out what the fatalities are at week 14. So we just type in F of 1,401, and we get a number. Clearly, we haven't had 0.0087 fatalities. That'll be one finger of one person or something like that. That's a proportion of the population. So what we should bear in mind is that the population of New Jersey is 9 million, roughly. So that would be 9 times 10 to the 6. So if we take the answer that we just got and multiply by 9E6, that's 9 million, that gives us a number, 7.8984, roughly 7.85 times 10 to the 4th. Now the key is the 10 to the 4th. That's 10,000. So right now that would represent 70,000 deaths. All right. We clearly have not had 70,000 deaths. All right. So that's more than a factor of 10 too high. So something must be wrong in our code to model the current situation. right? And I believe that the first fault lies in this initial proportion infected, right? So if we assume the initial proportion is 0.001, and we were to multiply that by the 9 million people in New Jersey, we would end up with 9,000 people initially infected, all right? That's probably high for what was going on 10 weeks ago, all right? Back at week 0, so that would be near the beginning of the year. We probably didn't have 9,000 infections in New Jersey. We probably had more. I'm just going to assume that we should add 2 zeros to I naught, and that would bring the number of infections in New Jersey down to 90 instead, all right? So if I add 2 zeros here to my I0 value, okay, that would start us at about 90 infections at the beginning of the year, 14 weeks ago. So if I run this now, we can see that at 14 weeks, we can't even see anything that's happening, all right? And the reason why is right now our graph is looking at the total population, right? So if we were to look at the total population, a very, very small percentage are actually infected, and fatalities are an even smaller percentage of that. So we can't see what's happening at week 14. We can see, though, this idea in the news, you're probably hearing about the idea of a second wave, right? It's possible that if we suppress the epidemic now, but then loosen up, we'll have a big wave later on, later in the year. So we'll talk about that second wave more in a little bit. What we need to do now is actually be able to see what's happening at week 14. And to see that, we have to change the Y max value. If we make it more than 100% of the population, we won't see what's going on right now. So let's bring that down to 1% of the population and see if we can see anything happening around week 14. There we go. Okay, so if we only look at 1% of the population, we can see the infections and the fatalities, and the fatalities barely show up because that's a very small number compared to our whole population. But we might have a more realistic number here. Let's go ahead and see what the fatalities are at week 14. And I'm going to multiply that by 9 million just to get a sense of the number. Now that number is probably a bit low. Okay, so we certainly have had more fatalities than that. So it's possible maybe the transmission rate is more than 3. Okay, we also, it turns out, I think that this TI value that I'm using is not very accurate. You may want to look that up and see how that TI value changes. So you probably want to play with I0, R1, and this TI value, maybe even this TE value, until you get a number of infections at week 14 that, I'm sorry, number of fatalities at week 14 that's similar to what we do have in New Jersey. So that would be a better model. I'm going to just assume that this is good enough for now. We probably have about 10 times that in fatalities now, maybe even a little bit more. So it will take some playing around with these parameters to get that approximately correct. All right, but what I wanted to show you is, okay, we have this very little spike out of the entire population. Now, when we do that, the second wave is occurring, and it gets huge compared to what we have now. And we can see what we have now is already a medical problem. So we wouldn't want our second wave to go off of the chart, right? Well, to keep the second wave from going off of the chart, I may need to change my R3 value. So let's bring that down to 1.5 and see what happens here. Okay, we can see that we're getting closer to being on the chart. We can also see, though, that a lot of interesting things, many interesting things are happening after 52 weeks. Let's extend 52 weeks, that's 1 year, out to 2 years, 104 weeks, and see what the graph looks like. Okay, so we can see that, oh, we must have had a peak in infections somewhere around, in the 60-week mark, is probably when we have a maximum of infections. And then it's dropping off and coming back down to close to zero by the time we reach 2 years, right? But still, that infection rate is high and the total fatalities are high. We can see that compared to the peak that we have now, that second wave was way too high. So let's bring that R3 value down further. Okay, in fact, let's look at how high that is. I'm going to make Y max. I'm going to go up to 2% of the population as my Y max. Oh, and we can almost see the peak of the curve. But clearly, if we get up there, we're in big trouble compared to where we are now. So we might want to, now we said the peak now is probably a little bit low. It's probably up here, a factor of 10 higher. So actually that might be about right for the second peak. But if we were to bring R3 down even further, let's make that 1.4, we can see that second wave effect is probably, it gets better and better, all right? So we might have a level that we would be able to handle medically. I'm just going to make the R1 value a little bit bigger, make it 3.5 to see if we can get our first peak to be more realistic. Okay, that is making our first peak a little more realistic. Maybe it was a little bit bigger original percentage of the population, so I'll bump that up a little bit. All right, and we can keep playing with the numbers until we get something that is a realistic model. But you don't want your second wave to get a lot higher than the first wave that we have now. Otherwise, we'll have more problems later. So how do we make the second wave not get so high? We keep bringing R3 down. Now that's good in terms of the health of everyone, but economically, that could be devastating to try to keep R3 that low. It's a balance between putting restrictions in that will keep us healthy or relatively healthy. There will be health issues regardless, unless we can bring R3 down well below 1, which would be very hard to do economically to keep that below 1. In fact, let's make it 1 and see what happens. So you can see that would be very good if we can keep R3 down to 1, but that would actually be very difficult to keep R3 at 1 while opening up the economy. So we're clearly not going to want R3 to be a number like 2, because we can see we go off of the chart with the second wave, trying to make it, and 2 is much less than the original infection rate. So that would still require some social distancing and better health practices. Maybe if we can do better testing and we can isolate people as soon as they do become infected, that would actually lower the R a lot without having to keep healthy people out of the economy. But maybe something like 1.2 is something we could achieve that would keep the second wave from being a problem. Okay, now you're hearing in the news all kinds of things about testing. With aggressive testing and tracing, people could begin to resume normal activity and be tested regularly. And as soon as somebody was shown to be infected, and if you could put them in quarantine, they would clearly no longer infect people. And you could maybe quarantine people who had been exposed to those who had been infected as well. So that's what they're talking about with contact tracing. We would be able to at least test everybody who had been exposed to the person who tested positive. We could quarantine the positive person, test everyone around them, and see if any of them are positive, and then make sure we quarantine every positive person, and then keep testing everyone who had been exposed to a positively tested person. So we could create a strict net that would make this R3 value lower, that might make everything work out. So you can change your numbers around, but see if you can make your numbers fit the data that's on the ground now.